Now look at salt. And salt is a topic that we tackled in details in Form 2. We even started in Form 1. We defined a saturated solution. We said that a saturated solution is one that cannot dissolve anymore at a given temperature. Now remember that temperature bit of it. Then in Form 2, we defined a salt is a substance form when the active hydrogen in an acid are replaced wholly or partially, directly or indirectly, by a metal or the ammonium ion. That is my working definition. You could have others, but at the end of the day, we want to replace the hydrogen in an acid. And that can be done by a metal, the ammonium ion. Then in the same topic, we learned how to prepare salt. And I don't want to go into that. Then we actually said that the method that is going to be used to prepare salt will depend on the solubility. And that was what I would refer to as a qualitative aspect of solubility. And those are the solubility rules. So we agreed that all nitrates will dissolve. That's easy. All nitrates, non-nitrate is insoluble. All carbonates, hydroxides and oxides, sulfites also, are insoluble apart from those of group 1 and the ammonium ion. That is the sodium, potassium, ammonia. Calcium hydroxide is slightly insoluble, as you've just said. The carbonate of aluminium and iron 3 do not exist. Then for the chloride and the sulfate, it was a bit interesting because not all of them are soluble or insoluble. So I've crafted some ways of helping us. You can come up with your own. We all know of a gentleman called Barak. So this is what I have said, that the super reader Barak can crap. Yeah, so the super reader, if you watch his speeches, maybe he craps a lot. Well, you can visualize that and use it to remember that super is for the sulfate, reader for lead, Barak for barium, can for calcium. Then crap, chloride, and that is the chloride that are insoluble as silver and lead. So for the sulfate, the insoluble sulfate are that of reader, read, Barak, barium, and calcium. But calcium sulfate is slightly soluble. The chloride that are insoluble are those of silver and lead. Now you could come up with your own way of remembering that, but that's the way that's what I use, so that I know that all sulfates apart from superreader, Barak and can, yeah. So lead, barium, and so you could use that. You could use that on any other way that you can use to remember that not all sulfates are insoluble. Not all sulfates are soluble. There are some insoluble. That's lead, barium, and calcium. Not all chlorides are soluble. There are some insoluble. Chloride and silver and lead. Now, so that is a qualitative aspect of solubility. But so to start us off, therefore, to build on what we've learned already, we shall look at the quantitative aspect of solubility. You want to quantify solubility. So that when we say that the sodium chloride dissolve because it's a group 1, then how much dissolve? In fact, that brings us to an interesting phenomenon. When we were in Form 2, we were told that all common salt of sodium, potassium, and ammonium are soluble. But when we went to the solvase process, do you remember what we were told? That when you mix the ammonia, when the ammonium chloride is mixed with the it's the sodium chloride mixed with the ammonium hydrogen, that is brine, plus the ammonium hydrogen carbonate that forms when I bubble ammonia through, when I mix the ammonia with the carbon 4 oxide. The two react to form insoluble sodium hydrogen carbonate. And I think there were question marks. You can ask yourself a question mark, a very big question mark, because if you are told that all common salt of sodium, potassium and ammonium are soluble, then how comes you are getting insoluble sodium hydrogen carbon? What makes this reaction possible? And that was a question you should have asked then. Now that you did not ask, then you don't have the opportunity to ask. But I could say that although it is soluble, it is not infinitely soluble. There is a limit to the amount that you can dissolve. You know that when you add sugar to water, you cannot dissolve everything. There will come a time when you cannot dissolve anymore. So we want to determine what time, that time when you say that no more can dissolve, that this solution is saturated. So there are two things that we shall need to quantify solubility. Now, I've always asked students some question here. That the solubility of solid A is 5 grams. The solubility of solid B is 20 grams. Then I asked them which one is more soluble. And they are in a hurry to tell me that B is more soluble. Then I go on to tell them the 5 grams dissolve in 10 grams of water. The 20 grams dissolves in 1,000 grams of water. Now, I think the question is different. The question is now a bit different. They were all wrong. They were all wrong. Because this one is dissolving in so much, in a very big, the amount of water is so much, as opposed to this one. So this one now it becomes more soluble. So in order to talk about solubility, there are two things that you shall need. One, you shall need the amount of solute that is dissolving. That is one. Number two, you must specify the amount of solvent. The amount of solvent. So this is the way we define solubility. It is the amount of solute, that dissolves in 100 grams of water at a given temperature. It's the amount of solute that will saturate. You need to make a saturated solution. 100 grams of water at a given temperature. Note, I talk about the solubility in 100 grams of water. Why do I stick to grams of water and not volume of water? Because volume is temperature dependent. So if I am talking about 100 grams cubic centimeters of solution, then I check to another temperature. The volume is no longer 100, it has increased a bit. So I have two variables, but you know that the mass will remain constant irrespective of the temperature, because I want to have only one variable, and that is the mass of the solid that is dissolving. Then I use the grams of water and not the volume of water. So solubility is the amount of substance that saturates 100 grams of water at a given temperature. You could talk about saturating 100 grams of a solvent, but mostly the solvent that we use is water. So 100 grams of water at a given temperature. So let us do an experiment. Of course, you can also give the solubility in moles per liter. We shall easily do that. Let us go on to perform a very simple experiment to determine the solubility of potassium nitrate at a given temperature. And this is going to be our procedure. We are going to take about 10 cubic centimeters of distilled water, about 10. I hope we are there. Then we shall add excess potassium nitrate. we shall warm this solution to around 40 degrees Celsius, but you need to pick up the exact temperature. Then we shall weigh, not that this, as we warm now, we have excess of the potassium nitrate. As we warm it, more of it is going to dissolve. But then when we get to exactly 40, we shall first weigh a watch glass. Then we shall extract some of this solution. And we shall have to do that very fast so that the temperature does not change. Because if the temperature decreases, we shall use the temperature that we get at this point. So the temperature must not decrease so much. So then we shall take a bit of this solution. It was about 10. We shall take a bit of it and weigh. Put it in a watch glass and weigh it again. We shall weigh that again. Then we shall proceed to evaporate on a water bath. Two reasons why we need to evaporate the resultant weight solution in a water bath. Number one, should we heat it directly, the potassium nitrate may decompose. But even before it decomposes, there is a process that is called spitting out. So when we are almost getting a solid, some of the potassium nitrate will jump out of the, for lack of a better term, it will jump out of the watch glass. So that is a process that we call spitting out. So to prevent spitting out, we shall heat on a water bath. That will be gentle heating. Then after that, we shall also weigh the watch glass with the resultant solid. We can look at a diagrammatic representation of that. What pieces of information do we need? The temperature of the solution, we need to pick it from the experiment. You can write that down. The mass of the watch glass need to be picked. The watch glass with the solution, you need to record that. You should be writing that. And also the watch glass with the solid after evaporation. You need to record that, because it is from that data then we shall be working out the solubility of potassium nitrate at that particular temperature. So let's go on to write that and look at the grip and pick up the data.
We'll take quite a bit of solid, even with rapid stirring. And of course, we don't know the temperature yet of the water, but we know that it started at around 50. There will be cooling due to the effect of the glassware, the stirring rod, and the potassium nitrate that's dissolving. So just one more measure there, and we've got a fairly concentrated, if not saturated, solution of potassium nitrate. Well, now we need to take that solution and pour it into our test tube here, so that it's about 2/3 full. And that tube needs to quickly go into the water bath, and we need it to equilibrate quite quickly. Now it's thin walled, so we shouldn't have much of a problem with that. Slurring a little there. The water bath is still decreasing at 48.5 degrees centigrade. The potassium nitrate may well not be saturated now. We'll just add a little in the top here, just to make sure we've got some solid in the bottom. And check with our thermometer what the temperature is there. So you might see the two thermometers, the thermometer in the water bath at 48, the thermometer in our test tube somewhat below that at the moment at 37 and rising. So let's leave that to equilibrate for a minute or two. The water bath externally, the red thermometer here reading 42.5, 42, and the solution in the test tube reading 42, 42.5. Well, that's not the critical phase in the experiment. The critical step is the next step. In this experiment, we're going to be using a watch glass to reduce the amount that we have to evaporate in the next step. So, first of all, we need to weigh the watch glass on the balance here, and we find that the mass is 25.52 grams, 25.52. Now the next step is absolutely critical. You've got to be rather quick at doing this, and it's as well to practice beforehand. So check the temperature. The temperature is 42. Remove the thermometer, and what we're aiming to do is to transfer quickly a small amount of the liquid at 42 degrees C onto the watch glass. Minimum amount. There we go. That's quite a splodge. And we'll re-weigh. It's now weighing 28.88 grams. 28.88. We've now finished with the water bath here, and we can remove it. And what we need is a boiling water bath, which we'll make in a small beaker here. We no longer need the clamp and stand. But we do need some more boiling water. So in that goes, 2/3 full. Remember to add a few anti-bumping granules into the water. In they go. Just one more should be enough. And the next stage is to get our solution on the watch glass evaporating to dryness. And we're going to do that by placing it over the water bath, which hopefully will bring rapidly to the boil. So on goes the solution. We have got rather a lot there, perhaps poured a little bit too much. Can't be helped at this stage. And it's worth knowing that potassium nitrate does decompose thermally at around 400 degrees centigrade, which is why we're heating gently with the water bath here. So the object of the exercise is to evaporate the solution on the watch glass to dryness, remove all the water, and then re-weigh on the balance. Perhaps could have done with a few more anti-bumping granules in there. So you may be able to detect here some white solid forming around the edge of the little pool of potassium nitrate, saturated potassium nitrate solution that we had, and that is of course solid potassium nitrate already crystallizing from the mixture. Okay, we'll start the stop clock, pause the video and see how long this takes to evaporate through to dryness.
Now this is a data that I got. Of course, I did not wait for the evaporation to be complete, so you may not have these. It is supposed to be 27.05. So if you can complete that, then you can pause at that point. Just write a 27.5, pause at that point, and work out the solubility of the potassium nitrate in grams per 100 grams of water. Now welcome back. I hope this is what you've done. You've first obtained the mass of potassium nitrate. How do you get the mass of potassium nitrate? You have the mass of the watch grass and the solid, that's the potassium nitrate. Then the mass of the watch grass are run. The watch grass and the solid and the watch grass. When you subtract, of course, the watch grass cancels, you are left with the mass of the solid, which is 1.53. Then I also need the mass of water. How do I get the mass of water? The watch grass and the solution. Solution contains water and the solid. Then the watch grass and the solid. That's the last, and then this one. When I subtract them, the grass and the grass, the solid and the solid, so I'm left with the mass of the water, which is 1.83. But solubility is supposed to be the mass per 100 grams of water. What do I have? 1.83 grams of water holds 1.53 grams of the solid. What about 100 grams of water? That is 83.6 grams per 100 grams of water. Of course, to three significant figures. But that is I hope that is also what you obtain. We can go on to get the solubility in moles per liter. What do I need to do? Just convert the 83.6 grams to moles. So I know the mass of 1 mole of potassium nitrate is all that. So I can convert the 83.6 grams to moles, and that is what I have. But these are moles per 100 grams of water. Solubility is in moles per liter of solution. So these moles are in 100 cubic centimeters of water, and I will consider the mass of the volume of the solution to be equal to the volume of water, because the solid has negligible volume. So this volume in these moles are in that 100 cubic centimeters. What about 1,000 cubic centimeters? All that capital M to 4 significant figures. And we can look at other examples. We are told that the solubility of potassium nitrate at 50 degrees Celsius is 85 grams per 100 grams of water. I think we have worked out something close to that. The first question is, what mass of potassium nitrate dissolves in 450 grams of water to make a saturated solution? Now note, I'm revisiting the solubility. 100 grams of water contains 85 grams. That is the interpretation of solubility. The mass in 100 grams of water. 100 grams of water contains 85. Now I am interested in the mass in 450 grams of water. The 450 grams of water. So if 100 contains 85, what about 450? And that is a simple ratios, and that gives me 352.5 grams of potassium nitrate. Grams of the salt, and it is only a question of it's simple ratio, but the mistake you'll make is if you put this side, you'll definitely make a mistake. But that is a mistake that is easily you cannot, as long as you write this water, salt, you will not make such a mistake. You will not make such a mistake. So let's try to do the next question. What does it read? The same solubility, 50 grams per 100 grams of water. So what mass of water is required to dissolve 38 grams of potassium nitrate? So just remember to put the potassium nitrate on its side, the water on its side, and you'll be able to do that question. You can pause and do that, and the answer will, you are expected to get 44.7 grams. You can easily do that. Next question. So 100 grams of a saturated potassium nitrate solution was evaporated to dryness. Determine the mass of the residue. The residue, of course, that is the mass of the potassium nitrate that was obtained. Now I have underlined one word here, solution, because we have 100 grams of the solution. We don't have 100 grams of potassium nitrate. We don't have 100 grams of water. So I therefore have to use the expression. I have to get the mass of solution. So it would be wrong to say 100 grams of water. 100 grams of water contain 85 grams of the solid. That is the solubility that is given. What about 100 grams of solution? What is wrong with that? Because this is solution, but that is water. That is water. The solubility is in 100 grams of water. So I must either get both of these as water or both of these as the solution. But I've chosen to make both of them as solution. How did I get the solution? If the solubility is 85 grams per 100 grams of water, so I take 100 grams of water, I add 85 grams of the solid. So what is the mass of the solution? It comes to 185. So 185 grams of solution now contain 85 grams of the solid. What about 100 grams of the solution? And it is as easy as it is, so I can easily get that as 45. You can use the same argument to get the mass of potassium nitrate that would be required to prepare 500 grams of the saturated solution again, of the saturated solution. You can pause and attempt that. Please ensure that your answer comes to 229.7 grams. Now another example. 20 cubic centimeters of a saturated sodium chloride solution at 25 required 18.2 cubic centimeters of 0.1 molar silver nitrate to precipitate all the chloride ions. Determine the solubility of the sodium chloride. Now when you read that question, you realize that there is a reaction that is taking place. The reaction between silver nitrate and sodium chloride to precipitate the silver chloride. Of course, it's going to form a solution of silver nitrate. So there is a reaction that is taking place. Now, whenever you have a reaction taking place, there is always going to be a three-step approach to doing that. There, you will identify a known, then get its mole. Now, the known will be, when you read the question, you'll ask yourself, what is the question about? In this case, this question is about sodium chloride. So sodium chloride becomes your unknown. It is not known. So the other one becomes your known. So in our case here, we should know everything about silver nitrate. So the first thing that you do, get the moles of silver nitrate. Get the moles of the known in general. Moles of the known. So from form 2, of course, most of the known, you can use the expression 1,000 cubic centimeters. 1,000 cubic centimeters contains 0.1 moles. It is 0.1 molar. That is what it means. 1,000 is 0.1. What about the volume is 18.2? So it comes to that. I should have over. So that I'm getting 0.00182 moles of the known. Now step number 2. Using the equation, get the moles of the unknown. And it is always going to be like that. Always. If you get a different one, come to me. You can refer to your school fees. How much is that? Now, so how do you get the moles of the unknown? Looking at that equation, the ratio is 1 to 1 to 1 to 1. So 1 mole of silver nitrate reacts with 1 mole of sodium chloride to form 1 mole of sodium nitrate and 1 mole of silver. So if you have 1 mole of that, you get 1 mole of that. If you have 2 moles of that, you get 2 moles of that. Now you have 0.00182 moles of the known, which is silver nitrate. You have so the moles of that are 0.00182. So how many moles of silver chloride should you have? Right, they should be the same because the ratio is 1 to 1. So that much. Now normally what you do after that is get the concentration. That is a normal process. But I don't need to get the concentration in this case. All I need to do is convert this now to mass. I have 1 mole is the relative formula mass expressed in grams. What about this number of moles that I have here? Now, these moles are in the volume used. So I now, and that is the other thing that you need to watch again. So the volume of the sodium chloride used is 20. So the moles required should be in the volume used. Moles required are in the volume used. Moles required in the volume used. So the 20 cubic centimeters of water, which I have equated to 20 grams, assuming that the density of the solution is 1 gram per cubic centimeter. So 20 grams of water, this solution is 20 grams, so contains this number of grams of that. Now you realize I did not subtract that because I have assumed that this mass of sodium chloride occupies negligible volume. So it did not, so if I have 20 grams, if I have 20 cubic centimeters of water, I add 0.10647, then the result, the volume will still be 20. The volume will still be 20 and not 20.1. Not 20.1 because this one occupies negligible volume. So unlike what I've been doing in the past, adding that to convert the volumes to volume of solid to mass of water, I don't subtract in this one because this solid occupies negligible volume. So the 20 grams of water will contain that, but what about 100 grams of water? How many grams? So that is 0.5324 grams per 100 grams of water at whatever temperature this experiment was carried out. And so note that when you have a reaction, there are 3 steps. Moles of the known. Yeah, so the question is not about this one. So this one I should know it. Moles of the unknown. Use the equation. Then those moles are in the volume used. And then you can go on to answer any question. Now have another example for us. Example 3. A saturated solution of potassium nitrate, potassium sulfate at 20 was found by calculating to be 0.6 molar. Calculate the solubility of the potassium sulfate. So this one doesn't have very many steps. You can work it out and get to 10.44. 10.44 grams per 100 grams of water. So in this case, I think all I need to do is to convert the 0.6 moles to grams of potassium sulfate. Get the mass of 1 mole, get the moles, the mass of these moles. Those will be in 1,000 grams of solution because they're concentration in moles per liter of solution. So in 1,000 grams of water. So what about 100? And it should be very straightforward.